Hello and welcome to this series of videos on the maths of Diophantus of Alexandria's Arithmetica. If you've watched the preceding videos, you'll know that I spent a lot of time emphasising how Diophantus problems call for a single solution, and that cunningly designed but essentially arbitrary substitutions are his way to get there. So very different from algebra, where we tend to keep things as general as possible so as not to miss out on possible solutions. In this video we're going to look at something that might at first seem to contradict everything I've been saying there. A special technique that generates an infinite family of solutions to a special problem, namely finding squares of rational numbers that are a given distance apart. Diophantus calls this technique double equating because it gives us a way to express both the larger and the smaller square in terms of our unknown symbol at the same time. So if we think about the difference of two squares geometrically for a second, it could be thought of as an L shape, and we can snip at the bend, rearrange into a rectangle, and see that the area of that L shape is the product of the difference in side lengths times the sum of the side lengths. It's the familiar factorisation of x squared minus y squared. Now imagine reversing that process. We start with the area of the rectangle, which we can take as 1, just for example. We first pick any factorisation of that area as the width and the height that are going to go into our rectangle. In general terms, s times 1 over s is a general factorisation for different positive values of s. We need the factors to be different to create an L, so we need s not to be 1. Then we can extract the side lengths of the two squares from the dimensions of the L shape. One is the average of the width and the height of the rectangle, while the other is half the difference, or the absolute value of that if it happens to be negative. So if we want to find two squares that are 1 apart, this method says, well, you can immediately say that those squares can be written as the average of s plus 1 over s squared and the average of s minus 1 over s squared for any positive rational value of s other than 1. Let's now look at one of Diophantus' problems and see why this method is more useful than the ones that we've seen before in videos 4 to 5. Our task is to find a positive rational that is both 2 and 3 less than squares of rational side. As we learned in video 5, what we do is we start with the squares rather than the rational that we're eventually aiming for, and we notice that they're 1 apart. So to find two squares that are 1 apart, what we would do using the preceding method that we've seen is say, let the smaller one be s, let the side of the larger one be something like 2s minus 1, then we get s squared plus 1 is 4s squared minus 4s plus 1. Those plus 1s were designed to cancel out to give helpful form, and we get s is 4/3. The squares become 16 over 9 and 25 over 9. It's great that they're 1 apart, but then the rational number that is 2 or 3 below those two squares is negative. It's minus 2/9, and Diophantus won't allow us to have a negative solution. So we've hit a stumbling block, and it was a reasonable go, this substitution that we made of 2s minus 1, but we need to fiddle around with it to try and replace the 2, for example, until we avoid the problem of a negative solution. And it's not really immediately obvious whether to increase the 2 or decrease it or what. Using modern techniques, you can analyse it a bit. You could draw a graph of the hyperbola y squared minus x squared is 1. Our substitution boils down to supposing that y equals 2x minus 1, so we look at where the hyperbola crosses that straight line, and we see that the blue line is too steep. It crosses before x equals root 2, and so equating the side of the larger square with something like 1.5s minus 1 should shift that line down a bit and do the trick and give us a positive solution. But Diophantus and his students couldn't do this kind of analysis. So let's leave it aside and concentrate on how the double equating method works for him. We need two squares that are 1 apart, and we need the smaller of those squares to be above 2. It's this constraint that really tells you the double equating method is the thing to use here. We factorise the difference 1 into s and 1 over s. The side of the smaller square is then going to be half of s minus 1 over s, and we need to make that sufficiently big. And we can do that just by making s big. We could choose s as 1,000,000 if we wanted to, but we need to keep the calculations reasonably simple as well. So let's make s something like 4. Then the smaller square becomes 15 over 8 squared, and the number 2 less than it we can easily calculate is 97 over 64. So basically the double equation method just gives us a lot of flexibility to avoid inadmissible solutions, negative solutions in this case, than the methods that we looked at before, which involve a bit more trial and error. Another advantage of being able to generate multiple solutions quickly by using different factorizations is apparent in the next problem we're going to look at, which is to find three distinct positive rationals such that their sum plus the square of any of them makes a square of rational side. Again, start by thinking about the squares. We've got 6 of them in this problem, and they fall into 3 pairs, each of them a set distance apart, that distance being the sum of the unknowns that we are eventually trying to find. We therefore want to set that distance to a number with 3 different factorizations that are relatively easy to work with. So if you think of the example of a number like 12, which has 3 nice easy factorizations, the double equating method would tell us that for each factorization, half the difference between the factors is the side of a square where we add on 12 and we get another square. So those half differences would be the unknowns in the problem. But there's a problem, an issue here, which is that the unknowns are not independent from the sum of the unknowns, which is what we started with assuming that it might be 12. And in fact, when we work through it, we find that they add up to 8. So we can't have 12 equals to 8, but what Diophantus does here, which is rather clever, is throw in the unknown symbol as a sort of scaling factor. If instead of saying the distance between the pairs of squares is 12, we say it's 12s squared, then the dual equating method gives us side lengths, and therefore unknowns, in terms of s. So the sum of the side lengths is something that we can express both in terms of s and as 12s squared. That equation is in helpful form, so we're going to get a rational solution out of it. In particular, we get 8s is 12s squared, s is 2/3, and the solution 11/3, 4/3, 1/3 to the original problem. The last problem that we're going to look at for this video again shows how to use the dual equating method where the distance between a pair of squares is not a constant but involves the unknown symbol. So we want to find 2 distinct positive rationals such that their product plus either of them or plus both of them, plus the sum, makes a square of rational side. What Diophantus does first here is the sort of thing we looked at in video 5. Just sort out one of the squares in a simple way and then try and focus on everything else in the problem. So he sets one unknown to s and the other to be 4s minus 1 because the product of that plus s is 4s squared, and we know that 4s squared is going to be a square whenever s is a rational number. So, it's going to be the square of a rational number whenever s is rational. So there's a bit of a leap of faith there. We just have to hope that later down the line we're going to be able to show that 4s squared plus 4s minus 1 and 4s squared plus 3s minus 1 are both squares for some value of s. Well, those are s apart. We've got 2 squares that are s apart, and the double equating method gives us a lot of flexibility. The key question to ask now is what factorization of s can we choose that is going to generate squares that have 4s squared in them that we can then cancel out and get into an equation in helpful form? And the answer is, well, we want the average of the factors to contain 2s, so when we square it, it's going to become 4s squared. So if you choose the factorization s is 4s times a quarter, the average of the factors is 2s plus an eighth. When we square it, we find the larger of the 2 squares, 4s squared plus 4s minus 1, is also the square of 2s plus an eighth, 4s squared plus s over 2 plus 1 over 64. That's in helpful form. We just rearrange it a bit and we find a solution. S is 65 over 224. So, as I said, it wasn't obvious when we first substituted in s and 4s minus 1 that the double equating method would actually work for us later down the line. But the more one practices with it and works through Diophantus problems, the easier it is to spot when it's likely that the double equating method is going to work. For example, here, when you've played around with it a bit, you see that because we've got 4s squared in the things that we're trying to equate with squares using the double equating method, because 4s squared is itself a square, it's easy to get it to come out of the double equating method and to cancel out. In other problems, things aren't so easy as that, and Diophantus has to do something like we saw in video 6, which is have a go, reflect on where it got stuck and didn't work, design a sub-problem to get himself unstuck, and then go ahead and solve the original problem using that. Well, the double equating method is the first thing we've looked at where Diophantus gives a whole parametric family of equations to a problem. And this is certainly a bit more like the drive towards general solutions in modern algebra. But as we've seen for Diophantus, even here it isn't really about expressing an infinite number of solutions in a general form. The method is just a particularly flexible tool to be used as a stepping stone in a wider problem with particular solutions in mind. And as usual, I've given you a few more of Diophantus problems here to practice on if you'd like to. As I mentioned at the end of video 6, the next video in this series is going to address Diophantus' use of scaling factors, something we've seen also in this video where we shifted from 12 as a difference between squares to 12s squared. If you'd like to be notified when I upload that and other videos in this series, do subscribe to the channel, and in the meantime, thank you very much for watching.